So question 2, we're into throwing the discus part 2. James releases the discus at an angle of 37 degrees to the horizontal. Describe the energy changes as it rises, falls, lands and rolls, coming to a stop. You may ignore any forces caused by the air. So ignoring air makes it a little bit easier because there's only one force acting on it as it goes through the air, and that's force due to gravity. Then when it hits the ground, there's a few forces involved, but it rolls along. So let's go. When it's rising, it's only the force due to gravity. So you'll start off with a maximum amount of kinetic energy that is slowly decreasing, so we'll put that decreasing, and you'll have increasing potential energy, gravitational potential energy. As it falls, so this is after the peak, so maybe it's helpful to consider this. So this is the rising section here, then we've got the falling section and the rolling section as it goes off after there. But the falling section, you've got temporarily, vertically, you've got just the horizontal kinetic energy from the horizontal movement, but vertically, you'll have the maximum gravitational potential energy. So that's gravitational potential energy. It's going to start to decrease, and kinetic energy will continue to increase from the top down. Kinetic energy will be a minimum at that top. That's quite important to note. It won't be zero because you've got the horizontal velocity constantly, continually, and yeah. Anyway, and then when it hits the ground and rolls, you've got no EP grav, no gravitational. It's meant to be a P grav, but you will have kinetic energy from the horizontal motion, and as it rolls, and friction and heat produced from that friction will gradually slow it down. So all of that energy will eventually come to heat, and then it stops. Okay, B, state the size and direction of the acceleration of the discus at its highest point in the trajectory. So right at the peak on the diagram below down there. So this is a little bit of a tricky question, sort of a trick question. It's actually constant. The acceleration is constant during the entire flight. But at the highest point in its trajectory, it's going to be the same. So it's going to be from the force being proportional to the acceleration, F equals ma. The size and direction is always down, so it's the down, and it's always, let's see, the it's the acceleration, so it's easy. Acceleration due to gravity, 9.8 meters per second. I was thinking we have to calculate the force, and do we know the mass, but we don't need to worry about that at this point. So 9.8 meters per second downwards always, and that's just what the acceleration due to gravity is. Yeah. Anything accelerating under gravitation on the Earth, in the Earth's gravitational field, will be gravity. Unless it's far enough out that gravity is dispersed. And another different story. Sidetrack, no sidetracks. C. Takes 2.4 seconds to return to the height at which it was released. So that's, oops, I need to go to this tool. So from there to there, no, and back down to there, so there's the height of release. So all the way down there takes 2.4 seconds. It's shown that James releases the discus at an angle of 37 degrees to the horizontal. Calculate the speed at which he releases the discus. Okay, so usually with projectile motion, I want to change colour, you like to use half the flight. And when you're dealing with the, excuse me, the time of flight, that is usually just for a vertical up and down. So that's 2.4 seconds in total. If we're just considering the second half of the flight, then we're considering the time down, which will be 1.2 seconds. Our final velocity is what we're going to be able to use, because our final velocity combined with the angle 37 degrees, we'll be able to use some trigonometry to find what that speed is which it releases the discus. So at the top of the flight, we know that the initial velocity is 0. We know g is 9.8 meters per second. So we can find Vf equals Vi plus At, which equals, because Vi is 0 at the top of the flight, A is 9.8 times by the time, which is 1.2. Excuse me, so That'll give us a VF of 11.76. I'm just reading that one off the answers, and that's meters per second. But now, here's our final velocity that we're looking for. We've got the vertical. This is our 11.76 there, and we have the angle from the horizontal 37 degrees, and that's actually the same as change colour so you can see it a bit better. It's actually the same as this angle here, 37 degrees, because of co-interior angles, or whatever they're called, angles on a parallel line, I don't know, but they're both 37 degrees. That's our right angle, and so we can use 11.76 and that 37 degrees to find out what the actual V that we're looking for is. So what's that? It's sine 37 degrees equals opposite over hypotenuse, which is 11.76 over the V that we're looking for. So that means V equals 11.76 over sine 37, and that gives us 19.5 meters per second. There we go. Is there another question? Yes, there is. D. In fact, there is a vertical force acting upwards on the discus called lift. Explain how this force would affect the horizontal distance travelled by the discus. Okay, well, that reduces, if there's a lift, it reduces the downward force, the downward net force. Okay, so sum of gravity, force due to gravity is decreased from F equals ma. We know that if the force is decreased, and for the same mass, that means the acceleration has to decrease. That means that it will take longer for the v, for the velocity to increase on the way down and to decrease on the way up. This means this is the main point that we're getting at, the time of flight will increase, which means the range will increase. So that's what they're after. That the lift force would increase the horizontal distance travelled because it decreases the downward acceleration due to gravity. Yeah, meaning the time of flight's longer, which means it's travelling through the air for longer.